So in 2003, we launched a pair of twin rovers, golf cart-sized rovers, solar-powered, to get the Mars program back to the surface. We intended them to last 90 days. Today, basically 5 3/4 years later, they're still going. Pretty good design by our engineers at JPL. These rovers, in moving at the pace of a giant tortoise, about an hour a day, that's their pace, have uncovered things about Mars that you could only see from the surface. First thing they learned, crawling along the edges of things like craters, there's the Opportunity rover, is that there is a history of water on Mars in all of the rocks. While it looks as dry as a bone, actually, if you look closer, this is the Victoria crater that we spent a year at, as seen as we started the drive around and went into the crater. We realized in the layers exposed in this crater and in some of these rocks are history of minerals that can only be made in the presence of water. We have no physical way, good old chemistry doesn't lie, to make them. So while Mars may look as parched as anything we'd ever want to think about today, the history of water is there in the rocks. And if we could go to places more interesting than these flat parking lots with a few craters, we could get to places where the history of water in the rocks could lead to preservational environments, the kind of which on Earth preserve evidence of life. So our next mission to Mars, I'll show you in a second, is actually after that. Can we go to places better than this that expose Mars so we can ask, could Mars have been alive? And if it was, what are the signatures? I mean, imagine that. Are we alone? No. There were the Martians, whatever the Martians look like. So here you see Odyssey crawling down into Victoria Crater. Today it's heading far south. This is one of the great success stories of robotic exploration. Although it took 5 years to go as far as a couple of men and women could go in a couple of days, we did it for the cost of a James Cameron movie, not for the cost of something bigger. So robotic exploration is important. Now this funny view, you might say is about as boring as you can see. This is the real Mars. Swales of dust-like dunes and patches of, we think, sulfate-rich rocks covering about 10 or 15% of the planet. This is the real Mars, the Mars that humans would interact with. Problem is, these little dunes of fine talcum powder stuff aren't too good for driving robots in. They can get stuck. We got stuck for 40 days in this stuff with Opportunity. We backed ourselves out and escaped. But we have to build better mobility systems so we don't get stuck on the real Mars. Now, this funny picture is one of my favorites. I thought I'd share with you for a minute. After driving around Mars in one place for a while, Spirit dug around its wheels. They're about this big, about a year ago, and discovered lots of basically silica in the soil. The white stuff is basically pure silica, leached out of rocks by the action of water. So in this dry place, perhaps less interesting than where Opportunity's been in Meridiani, we've uncovered the signature of water. We found minerals like goethite, for those of you that like minerals, again, made in the presence of water, typically on Earth, we think on Mars. So the dry Mars we see from remote sensing, from orbit, is actually telling us a history of water on a planet that I would call a water planet. Today, the history of water on Mars is masked by rocks like these that are typical volcanic rocks. These are basaltic rocks, we think. And so it's beguiling, as Shakespeare once said. So it's important to remember, every time we've gone to Mars, we thought we got it. Yep, Viking going to Mars, going to find life. Nope, not there. Go back to Mars, again with other missions, and this is the launch of our Mars Reconnaissance Orbiter, and we thought we'd see something, and we got something else. So in 2005, we launched the MRO, the Mars Reconnaissance Orbiter. And this was one of my dreams, to go to Mars with the kind of eyes and spectrometers that could see Mars as if we were walking on the surface. And MRO got to Mars. It has a big 65-centimeter optic flying right down it there. And it arrived at Mars, and it changed the way we see the planet. Typically, we see Mars at this scale, craters. Then, thanks to the Mars Global Surveyor, we saw Mars at this scale. Now, we see Mars, if you look in at the next frame, for now 20,000 places, not at this scale. This is the typical scale that we get from the MRO, but at that scale. We can now fly over the surface of Mars for tens of thousands of places as if you were in a helicopter zipping over. At that scale, geology can become definitive. And this happens to be a gully site where these gullies once erupted fluids, Newtonian fluids, probably water. We don't absolutely know. They're stained by dust. But we've discovered more than 6,000 of these kinds of gullies, some of which have changed in the course of the last couple years. This is the polar ice cap of Mars showing the chock-a-block terrain. And this white thing you see here is a little patch of ice exposed. We do this routinely. So MRO has changed the way we see the planet. The other thing we've done with MRO is used a radar sounding method to slice right through the polar ice caps. What do they look like? And so using 20 megahertz wavelength radar, built in this case for us by our friends in Italy, we've been able to slice through sort of the way MRIs do our body and see the layering structure of the polar ice caps of Mars. They're about 3 kilometers thick. They have layers hundreds of meters thick. They run a scale the length of half the United States. This shows what we thought was happening, that in fact these ice caps are built up episodically. And that's a really important discovery. Within these layers could be lenses of preserved liquid water. Those could be the places where you'd want to go to seek signs of active life. Finally, we've also found in equatorial areas near the equator of Mars, with imaging and radar, that under the dust cover there are buried glaciers, tropical mountain glaciers near the equator on Mars. So, MRO, the Mars Express, the Mars Exploration Rovers, the Mars Global Surveyor, they have changed how we see the planet. We would now describe Mars as a water planet that could have preserved the biological signatures in rocks of life. Let me turn to Phoenix. In 2003, NASA said, okay, world community, all of you could have bid. We're going to have a competition like the Olympics to pick the next mission to Mars, Mars Scout. And after a year and a half of competition, a landed spacecraft developed at Lockheed Martin and Jet Propulsion Lab in Arizona went to Mars to ask, what is the ice really like up near the North Polar Cap? Why would we care about it? So it landed, it popped up its cameras, and it observed Mars for a period of 150 days from the edge of the North Polar ice cap. And during descent, we watched the descent through the eyes of MRO. And there is the parachute with the lander seen from another spacecraft as it descended. The geometry of that was rather challenging, but we actually managed to pull it off. We landed, this is the foot pad, and right underneath the lander, after the landing rockets settled, we found a patch of ice. Now this is what the North Polar region of Mars looks like. In the far distance, you can see the sun setting during the 150 days. As we went from summer to fall, we watched the wind blow. We tracked the star with lasers, the sky with lasers, and we saw patches of ice exposed and evaporate as part of our measurements. We ingested materials and detected for the first time definitively the molecule water on Mars with a chemistry lab. There's a patch of ice under the lander. So Mars, where we thought there would be ice, we validated it's there. If you start to look at the little white tinge here, that's frost forming on the surface as we come out of Mars' northern summer. So the winter sun set, it got cold, the solar panels got no light, the batteries died, and the mission essentially froze. But we generated 100 gigabytes of data in a 150-day mission for the price of a small blockbuster movie. There's the Wall-E-like camera eyes saying goodbye to you from Mars. Our next mission to Mars is the one I'm most excited about. And I get excited pretty easily, as you can probably tell. We've been dreaming of this since 2000. When we broke the program for Mars, we dreamt of sending an astrobiological rover to Mars. In this case, that we will land in the summer of 2012 with a rocket-powered helicopter system known as a Sky Crane, developed at our Jet Propulsion Lab. This rover is as massive as a Mini Cooper car. How many of you have ever been in a Mini Cooper? No? Yes? A few hands? Okay. They're not tiny, right? I mean, football players might not prefer them. But anyway, we will not even land the spacecraft that gets us there. We will drop the rover down on a winch, and then we will measure rocks without even going to them. By firing a laser beam and ionizing the surface of a rock, we will measure what they're made of. This is, like Star Trek does Mars. That will help us not have to drive everywhere. We will drill up to this deep into rocks, and then bring the samples, sort of with this crazy-looking extrusion process. Reminds me of my dog, but anyway. Bring materials into the vehicle. And inside the vehicle, here at Goddard, we've built something called SAM. And everyone asked me why Paul named it SAM. Could have been Sue. Could have been Jim. But SAM is the Surface Analysis of Mars package that will allow us to measure chemically whether there are the biological building blocks of life. We can actually measure the carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur in soils and in the air at levels that are better than those we could measure in labs when I was in graduate school. And now we have a robot lab we've developed right here that does all this stuff you see flying by. This is the X-ray diffraction part of it that tells how rocks are put together. This vehicle will launch next November. It weighs about 700 kilograms, 1,400 pounds. We will land it with the most powerful system, and the imaging system at the top, I'll just point to it up there, is inspired by James Cameron's 3D vision that he used to film Avatar. Actually, Cameron's on the team.